तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the 6th lecture in Module 3 on analysis of members. In today's lecture, we shall study analysis of members under flexure, specifically analysis for ultimate strength of partially prestressed section and unbonded post-tension beam. We shall also look into the analysis of behavior of members. First, we are studying analysis of partially prestressed section. The analysis that are presented earlier are for sections which does not have any conventional non-prestressed reinforcement. Usually, conventional reinforcement is provided in addition to the prestressing steel. When this reinforcement is considered in the flexural capacity, the section is termed as partially prestressed section. That means we do have conventional reinforcement in a prestressed beam most of the times, and if such reinforcement is considered for the capacity, then we term that section to be a partially prestressed section. Next, what are the reasons for using a partially prestressed section? The reasons are as follows. First, a partially prestressed section is economical compared to a fully prestressed section. We do not need as much amount of prestressing steel and anchorage units as compared to a fully prestressed section. Second, the cambering is less compared to an equivalent section without conventional reinforcement. We had seen earlier that when the prestress is transferred to a beam, then the beam tends to deflect upwards. That is called camber. This camber is large for beams with higher prestress. For a partially prestressed section, this camber is lower, and hence any effect of cracking due to camber is reduced in a partially prestressed section. The third reason for using a partially prestressed section is that the ductility is more in such a section. Today, towards the end of the lecture, we shall study about ductility. The fourth reason is that any reversal of moments in the beam, for example due to an earthquake, this is not detrimental in a partially prestressed beam as compared to an equivalent section without conventional reinforcement. In a completely prestressed beam, the prestressing is designed for a certain value of the moment in a certain direction of the load acting on the beam. But in case if there is any reversal of the moment, then the section is prone to premature failure compared to a reinforced concrete beam. A partially prestressed section is somewhere in between a fully prestressed section and a reinforced section. That means in a partially prestressed section, we try to have a balance between the benefits of a reinforced section and a prestressed concrete section. Depending on the situation, the partial prestressing is used. A partial prestressed section can be analyzed either as a rectangular or flange section. In our previous lectures, we had studied the analysis of fully prestressed sections for rectangular and flange sections. We analyze a section as a flange section when the flanges are in compression and the depth of neutral axis is larger than the depth of the flange. In a partially prestressed section also, we can have either a rectangular section or a flange section. Also, a section can be doubly reinforced with reinforcement near the compression phase. We had earlier known about singly reinforced section and doubly reinforced section in conventional reinforced concrete, and we see that a similar thing is possible in a partially prestressed member also. That means we can have reinforcement in the tension phase as well as reinforcement near the compression phase. Now, in this lecture, we shall study the analysis of a rectangular doubly reinforced partially prestressed section. The following sketch shows the beam cross section, strain profile, stress diagram and force couples at the ultimate state for a partially prestressed section. As we have come to know earlier that in the analysis at ultimate, first we start with the strain diagram. The failure is defined as the strain in the extreme compression fiber to be equal to 0.0035. With that basis, we draw a linearly varying strain diagram based on the principle sections remain plane till ultimate. We identify the strains at the different levels of the steel. For the partially prestressed section, we are having AS prime as the steel near the compression phase, which is at a depth D prime. We have the prestressing tendon, which is represented as AP, and its CGS lies at a depth DP. We also have the steel near the tension phase, which is represented as AS, and its centroid is at a depth of D from the compression phase. Thus, for this section, we have 3 layers of steel, and for each layer of steel, we can identify the strains from the strain diagram, and the strains are represented as epsilon S prime for the steel near the compression phase, epsilon S for the steel near the tension phase, and for the prestressing steel, we have a permanent component which is represented as epsilon DEC, which is the difference between the strain in the prestressing steel and the concrete, which exists throughout the loading of the beam. And then when we add the strain in the concrete at the level of the CGS to epsilon DEC, we get the total strain in the prestressing tendon, and the total strain is represented as epsilon PU for the ultimate state. From the strain diagram, we are moving on to the stress diagram, where we calculate the stress block for concrete and the stresses for the 3 steels from the constitutive relationships. For the stress in the concrete, we see that it is a parabolic diagram based on the design curve, and with a maximum stress of 0.447 FCK. The strain and the stress in the compression steel is represented as Fs prime, which we calculate from the strain epsilon S prime. The stress in the tension steel is represented as Fs, which we calculate from the strain epsilon S. And the stress in the prestressing tendon is Fpu, which we calculate from the total strain in the prestressing steel, which is epsilon Pu. From the stress diagram, we move to the force diagram. Cs prime is the force acting in the compression steel. Cc is the force which is the resultant of the stress block in the concrete. It is the compression carried by the concrete. Tp is the tension carried by the prestressing steel, and Ts is the tension carried by the reinforcement steel near the tension phase. The expression of the forces are as follows. Cs prime is equal to As prime times Fs prime. Cc is equal to 0.36 times Fck times Xu times P. This expression comes from the stress block, which we can calculate from the design stress strain curve. Tp is equal to Ap times Fpu, and Ts is equal to As times Fs. That means here we have the expressions of all the four forces acting in the section. Next, we write the equations based on the principles of mechanics. First, the equations of equilibrium. We write the equation for the longitudinal forces. Sigma F is equal to 0, which gives the total tension is equal to the total compression, and the tension constitutes of Tp, the tension in the prestressing tendon, and Ts, which is the tension in the reinforcement steel near the tension phase. The compression also consists of two components, Cc, which is the component taken by the concrete, and Cs prime, which is the compression taken by the compression steel. And we are writing the expressions of the individual forces, and this gives us the first equilibrium equation, which is for the longitudinal forces in the section. The second equilibrium equation is for the moment. Now here we are writing the moment with respect to the axis passing through the CGS. The moment at ultimate is represented as MUR, or ultimate moment of resistance, that is equal to the summation of the individual forces times the lever arm. The first term is Ts, which is the tension in the steel near the tension phase, times d minus dp, that is the lever arm between the tension steel and the CGS, plus Cc times dp minus 0.42 xu. dp minus 0.42 xu is the lever arm between the CGS and the resultant of the compression in concrete, plus Cs prime times dp minus d prime, which is the lever arm between the CGS and the centroid of the reinforcement steel near the compression phase. Once we substitute the expressions of Ts, Cc, Cs prime from the previous equations we have seen, we get an expression of the ultimate moment of resistance. Thus, this equation will help us to calculate the ultimate moment of resistance for a partially prestressed section. The second principle that we use is the equations of compatibility of strains. For each layer of steel, there is a compatibility equation. The compatibility means that the concrete and steel are deforming together. If there are distributed reinforcing bars in several layers and the spacing between the layers is large, then the use of compatibility equation for each layer is more accurate than the use of one compatibility equation for the centroid of the layers. The equations that we shall learn now will help us to analyze any beam where we have distributed steel in several layers with wide spacing between the layers. For each layer, we have a compatibility equation. In this figure, we can see that there are 3 layers of steel. The top layer is the steel near the compression phase. Then we have the prestressing steel, which is at a depth dP, and finally we have the steel near the tension phase. The first equation is related with the prestressing steel. The depth of the neutral axis, which is represented as xu, that divided by dP is equal to 0.0035, which is the end of the top triangle, divided by 0.0035 plus epsilon pu minus epsilon dEc, which is the end of the triangle which ends at the level of the prestressing steel. The second equation is related with the steel near the tension phase, which is given as d minus xu, which is the depth of the steel from the neutral axis, divided by xu is equal to epsilon s divided by 0.0035. And the third is the equation for the steel near the compression phase, which is xu minus d prime, which is the distance of the compression steel from the neutral axis, divided by xu is equal to epsilon s prime and divided by 0.0035. All these equations are from the similarity of triangles, and we see that we have got one equation for each layer of steel. Next, we are moving on to the constitutive relationships. The constitutive relationships relate the stress and strain in a material. For concrete, the constitutive relationship is considered in the expression of Cc, which we had seen earlier. This is based on the area under the design stress strain curve for concrete under compression. Here we see that the design stress strain curve has a maximum stress of 0.00447 FCK, and the maximum strain is epsilon Cu, which is equal to 0.0035. When we calculate the area under the design curve, we get the expression of Cc, which is equal to 0.36 FCK times Xu times B. The second constitutive relationship is for the prestressing steel, where the relationship is denoted by a function f1. Fpu is equal to f1 of epsilon pu. This function is available from the design curve for the prestressing steel, and this curve also we had seen earlier. The third constitutive relationship is for the reinforcing steel of the 2 layers. The equation for the bottom layer near the tension phase is represented as Fs is equal to function F2 of the strain epsilon s, and the stress in the steel near the compression phase is equal to Fs prime is equal to F3 of the strain epsilon s prime. Both the functions F2 and F3 are same if we are using the same grade of steel for the bottom steel and the top steel. For mild steel bars, the curve that we use is an elastoplastic curve. That means in the original characteristic curve we have an elastic region, then we have a plastic region, and then we have a strain hardening region. But the design curve that we use in our analysis is an elastoplastic curve without any strain hardening. The functional forms of both F2 and F3 are same if we use the same grade of steel. Thus, the strain hardening is neglected and an elastoplastic relationship is considered for mild steel. Usually, the strains epsilon s and epsilon s prime are larger than the yield value. Therefore, Fs prime is equal to 0.87 Fy and Fs is equal to 0.87 Fy when we have yielding in the steel near the compression and the tension phases. Now, in an analysis, the following variables are given. We know the geometric variables like B, which is the breadth of the section, D, depth of the centroid of the reinforcing steel near the tension side, D prime, depth of the centroid of the reinforcing steel near the compression side, dP, depth of the centroid of prestressing steel, or which is also denoted as CGS. We know the cross-sectional areas. Area of the reinforcing steel in the tension side is represented as AS. AS prime is the area of the reinforcing steel in the compression side, and AP is the area of the prestressing steel. Epsilon DEC is known from the amount of prestressing. This is the strain in the prestressing steel at decompression of concrete. In our previous lecture, we had studied how to calculate epsilon DEC. The expression of epsilon DEC for a pre-tension beam is different from a post-tension beam. For a pre-tension beam, epsilon DEC is the same as the strain in the steel just before the transfer of the prestress, but for a post-tension beam, epsilon DEC is the strain in the prestressing steel plus the strain in the concrete after the prestressing operation has been done. We also know the material properties. FCK is the characteristic compressive strength of concrete, Fy is the characteristic yield stress of the reinforcing steel, and FPK is the characteristic tensile strength of the prestressing steel. Now, what are the unknown quantities? The first unknown quantity is MUR, which is the ultimate moment capacity. The second unknown quantity is XU, the depth of the neutral axis at ultimate. We also do not know epsilon S, the strain in reinforcing steel at ultimate in the tension side. Epsilon S is the strain in the reinforcing steel at ultimate in the compression side, and epsilon PU is the prestressing steel at the level of CGS at ultimate. We also do not know the stresses in the steels. Stress in reinforcing steel for the tension side at ultimate is denoted as Fs. Stress in the reinforcing steel in the compression side at ultimate is denoted as Fs prime, and stress in the prestressing steel at ultimate is denoted as FPU. Now, with this set of known quantities and unknown quantities, the objective of an analysis is to find out MUR, the ultimate moment capacity. Now, the set of equations can be solved iteratively by the method of strain compatibility, as we had learned for a fully prestressed section. First, we are assuming the depth of the neutral axis, which is XU. From there, we are calculating epsilon PU from equation 3F7, where the equation has been rewritten as epsilon PU is equal to 0.0035 divided by XU by D minus 0.0035 plus epsilon DEC. Once we know epsilon PU, we next calculate FPU from equation 3F10, which is the constitutive relationship for the prestressing tendon. FPU is equal to F1 times epsilon PU. Next, we calculate the tension in the prestressing steel, which is given as TU is equal to AP times FPU. We calculate the strain in the reinforcement near the tension phase. Epsilon S is equal to 0.0035 D minus XU divided by XU. We calculate the stress in the reinforcement from equation 3F11. Fs is equal to F2 of epsilon S, and we calculate the tension in the in the reinforcement steel at the tension phase, which is equal to Ts is equal to As times Fs. Finally, we calculate the strain in the steel close to the compression phase, which is given as epsilon S prime is equal to 0.0035 times xu minus d prime divided by xu. We are calculating Fs prime from equation 3f12, which is given as Fs prime is equal to F3 of epsilon S prime. And finally, we are calculating the compression carried by the steel near the compression phase, which is Cs prime equal to As prime times Fs prime. Thus, what we did till now is from the compatibility equations, we calculated the strain in each layer of the steel. From the strain, we calculated the stresses from the constitutive relationships, and from the stresses, we calculated the forces carried by each layer of steel. Next, we are checking the equilibrium equation. Before that, we are also calculating the compression in the concrete Cc from equation 3f2. Cc is equal to 0.36 FCK XU times P. Now, when we are checking the equilibrium equation Tu is equal to Cu, if this equation is not satisfied, then we need to change Xu, our assumed value. If Tu is less than Xu, decrease Xu. If Tu is greater than Cu, then increase Xu. Thus, if the tension is less compared to the compression, then we need to reduce Xu such that the amount of compression going to the concrete is less and the stress coming to the steel is more. On the other hand, if the tension comes out to be larger than Cu, then we need to increase Xu, thus having more compression in the concrete and lesser tension in the steel. Like that, we iterate till the first equilibrium equation is satisfied within tolerable limits. Next, we are calculating MUR from the second equilibrium equation. MUR is equal to Ts times d minus dp plus Cc times dp minus 0.42 XU plus Cs prime times dp minus d prime. Thus, MUR consists of three components, which comes from the three forces having a lever arm with respect to the CGS. We are calculating MUR with respect to the CGS. Now, once we have calculated the capacity MUR, we compare it with the demand under the ultimate loads. Thus, our objective of the analysis is satisfied at this step. Next, we are moving on to analysis of unbonded post-tension beam. In an unbonded post-tension beam, the ducts are not grouted. Hence, there is no strain compatibility between the steel of the tendons and the concrete at a section. The compatibility is in terms of deformation over the length of the member. A sectional analysis is not possible. The analysis involves integrating the strain in concrete to calculate the deformation over the length of the member. Till now, whatever we have studied is for a bonded tendon, and we have assumed a perfect bond between the steel and the concrete, from which we wrote the strain compatibility equations. A perfect bond means that there is a relationship between the strain in the steel with the strain in the concrete at the level of the steel. Now, if the tendons are not grouted, then we cannot apply this strain compatibility equation, and we cannot use a sectional analysis. A sectional analysis means an analysis based on the strain, stress and forces at a section, because since the strain in the concrete at the level of the prestressing steel and the strain in the prestressing steel are not related by a one equation throughout the loading, we cannot use the conventional analysis for a bonded tendon. Thus, for an unbonded tendon, we write the equation, compatibility equation, in a different way. We write the compatibility in terms of the total deformation of the concrete at the level of the prestressing steel and the deformation of the prestressing steel. Hence, since we need to calculate the deformation of the concrete throughout the length of the member, we need to integrate the strain in the concrete at the level of the prestressing steel. The equation of compatibility is given as follows: delta P is equal to delta Cp, where delta P is the deformation of the tendon, delta Cp is equal to deformation of the concrete at the level of the prestressing steel, which is the CGS. The change in stress in steel, which is denoted as delta Fp at ultimate, is determined from delta P. The stress in steel at ultimate is given by the sum of the effective prestress Fpe and delta Fp. Thus, unlike the bonded tendons, where we calculated the stress from the strain at a particular location, here we are calculating the stress from the total deformation. Once we know the total deformation, we know the change in the stress in the prestressing tendon at ultimate, and then we calculate the total stress in the prestressing tendon at ultimate, which is equal to the stress at effective prestress plus the change in the stress, which is denoted as delta Fp. Thus, Fpu is equal to Fpe plus delta Fp. The value of Fpu for an unbonded tendon is less than that for a bonded tendon. We had seen earlier that for a bonded tendon, the stress at the cracks can get substantially high, whereas for an unbonded tendon, the stress is averaged out throughout the length of the member, and hence when the member fails, the stress does not reach a value which a bonded tendon achieves. Once we know Fpu, the ultimate moment is given by the conventional equation MUR is equal to AP times Fpu times the lever arm d minus 0.42 XU. The rigorous method of evaluating Fpu based on deformation compatibility is difficult. IS 1343-1980 allows to calculate Fpu and XU approximately from table 12 appendix B based on the amount of prestressing steel. The latter is expressed as the reinforcement index omega p is equal to AP times Fpk divided by BD FCK. The variables are given for three values of effective span to effective depth ratio, which is denoted as L by D. As we had seen for bonded tendons, that the code allows us to use some approximate values for the depth of the neutral axis at ultimate XU and for the steel stress at ultimate Fpu. For a bonded tendon, the tables were given in terms of reinforcement index, where Fpu was normalized with respect to 0.87 Fpk, the maximum allowed stress in the bonded tendons. For an unbonded tendon, the steel stress is normalized with respect to the effective prestress, and the table is again given in the with respect to the reinforcement index, which is the ratio of AP times Fpk divided by BD times FCK. Now, the values of Fpu by Fpe is dependent on the integration over the full length, and since the length can vary, the code has given the values for 3 values of the length, which is again normalized with respect to the effective depth of the prestressing tendon. There are 3 values of L by D equal to 30, 20 and 10, and for these 3 values of L by D, the variation of FPU by FPE is shown. And what we can see that with increasing amount of the prestressing steel, FPU decreases, and this follows the logic that the more steel we have, the less stress it will carry at ultimate. The other table gives us the value of the depth of the neutral axis, which is normalized with respect to the depth of the prestressing steel. XU by D increases with omega p. That means the more steel we have, we need to have a larger depth of the neutral axis to have higher compression in the concrete to balance the stress in the steel at ultimate. Here also the values are given for 3 L by D ratios, 30, 20 and 10. Next, we are moving on to the analysis of behavior of a prestressed member. The analysis of behavior refers to the determination of the complete moment versus curvature behavior of the section. The analysis at transfer, under service loads and for ultimate strength correspond to 3 instants in the above behavior. Till now, for the analysis of members under flexure, first we had studied the analysis at transfer and service loads, which is similar based on the elastic analysis, and then we had studied the analysis at ultimate. For the analysis at transfer and service, we had checked the stresses to be within the allowable stresses, and for the analysis at ultimate, we found out the ultimate moment of resistance, and we compared this capacity with the demand under factored loads. In both this type of analysis, we were interested only in the stress or the strength. But when we talk of analysis of behavior, we are interested not only on the stress or strength, we are also interested in the deformation of the member, which is given in terms of curvature. That means the analysis of behavior refers to the generation of the moment versus curvature curve for a section. The analysis that we have studied till now, the analysis at transfer, at service and for the ultimate strength, these are just 3 instants in the complete moment versus curvature curve for a section. How do we define curvature for a beam? The curvature, which is denoted as phi, is defined as the gradient of the strain profile. Phi is equal to epsilon c plus epsilon Cp divided by d, where epsilon c is the extreme concrete compressive strain and epsilon Cp is the strain in concrete at the level of prestressing steel or the CGS, and d is the depth of CGS. Remember that we are talking of curvature not just at ultimate, but throughout the loading history, and hence here epsilon c is variable. It varies from a 0 value till a value of 0.0035 at failure as the load is increased. This sketch shows the definition of curvature, which is equal to the gradient of the strain profile. For a rectangular section, if epsilon c is the strain in the concrete at the extreme compressive phase and epsilon Cp is the strain in the concrete at the level of the CGS, then the curvature is given as the sum of these 2 values, epsilon c plus epsilon Cp divided by d, which is thus the gradient of the strain profile. The analysis involves three principles of mechanics. First, the equilibrium of internal forces with the external loads at any point of the behavior. There are two equilibrium equations, A, the force equilibrium equation, B, moment equilibrium equation. Earlier in our analysis for ultimate strength, we had come across these equilibrium equations at ultimate, but now we are saying that the equilibrium is maintained throughout the loading history. That means at any point of the loading history, the longitudinal forces are under equilibrium and the internal moment is equal to the externally applied moment. The internal forces in concrete and steel are evaluated based on the respective strains, cross-sectional areas and the constitutive relationships. The second principle that we use is the compatibility of the strains in concrete and in steel for bonded tendons. This assumes a perfect bond between the two materials. Thus, to relate the strains in the several layers of steel with the strain in the concrete, we use the strain compatibility equation. For a bonded tendon, a perfect bond is assumed. If we have an unbonded tendon, then the strain compatibility equation cannot be used as we use for a bonded tendon. For an unbonded tendon, we use the compatibility in terms of deformation. The third principle that we use is the constitutive relationships relating the stresses and strains in the materials. These relationships are developed based on the material properties. The equilibrium and compatibility equations and the constitutive relationships can be solved to develop the moment versus curvature curve for a section. In this lecture, we are not going into the details of evaluating the moment versus curvature curve, but we are just learning the basic idea of how to develop the moment versus curvature curve. That means we have a set of equations which are written based on the principles of mechanics. Then we solve those equations iteratively with an increasing amount of a certain variable, say the maximum compressive strain in concrete. Now, once we solve the set of equation for each value of epsilon c, we get the complete moment versus deformation curve. The following plot shows the curves for a prestressed and a non-prestressed section. The two sections are equivalent in their ultimate flexural strengths. The idea of studying the behavior is to understand the effect of prestressing in the moment versus curvature curve in a section. For a conventional reinforced concrete section, which is non-prestressed, the initial part we have an elastic behavior where the moment is proportional to the curvature. Then after cracking, there is an increase in the curvature, and then there is nonlinearity in the moment versus curvature curve, which is not as much as we see after the yielding of the steel. At the yielding of the steel, we can get a sharp kink in the moment versus curvature curve if we are using mild steel, and after the yielding we see a plateau of the moment versus curvature curve, and this curve goes up to the point when the extreme strain in the concrete reaches a value 0.0035. On the other hand, for a prestressed section, we see that the curve has been shifted from the origin. We have a higher cracking load for a prestressed section, and then after cracking we have an yielding of the steel, but here we do not see any sharp kink in the curve because the prestressing steel does not have a specific yield point. And finally, the strength in the prestressing steel also tapers off to a maximum value. Now we are comparing the curves of two sections whose ultimate strength are same. Now, from this plot, the following can be inferred. First, the prestressing increases the cracking load. This is the primary reason why we use prestressing in a reinforced concrete section. The increase in the cracking load leads to the following benefits. First, it leads to the reduction of steel corrosion, in effect which increases the durability of a section. Second, full section is utilized. That means we have a higher moment of inertia for a prestressed section corresponding to a reinforced section, which gives higher stiffness, and thus we have less deformations in a prestressed concrete section of equivalent strength, and thus it gives improved serviceability. Also, since the section is uncracked, we have increase in shear capacity for the prestressed section. The second observation is that prestressing shifts the curve from the origin, which means for the prestressed member there is a negative curvature causing camber in absence of external moment. We had seen earlier that when the prestress is transferred to the concrete member, the member bends up. That means now it has a negative curvature in absence of any external load. Even the self weight may not be adequate to bring it down. That means although the self weight is acting downwards, still due to prestressing the member may hog up, causing camber. A certain amount of external moment is required to straighten the member. That means we need some external load to have zero curvature in a prestressed member, whereas in a reinforced concrete member the curvature is zero in absence of any external load. The third observation is, for a given moment the curvature of the prestressed member is smaller. If we go back to this curve and if we look at the two values of the curvature at a particular value of the moment, we see that the curvature in the prestressed concrete member is less than the curvature of the reinforced concrete member. Hence, prestressing reduces curvature at service loads, which gives less deflection at service loads. The fourth inference is, for a given reverse moment, the curvature of the prestressed member is larger. That means in case if the moment reverses, then the curvature of the prestressed concrete member will be higher than that in a reinforced concrete section. We can conclude that prestressing is detrimental for the response under reverse moment. Finally, we see that the ultimate strength of the prestressed member is lower for reverse moments, and hence prestressing is detrimental under reverse moments. Our sixth inference is, for a partially prestressed section with the same ultimate strength, the moment versus curvature curve will lie in between the curves of prestressed and non-prestressed sections. Thus, for a partially prestressed section, we may get the benefits of both a reinforced concrete section and a prestressed concrete section depending on the amount of prestressing. For a partially prestressed section, the cracking moment will be higher compared to a reinforced concrete section, but in case if there is a reversal in the moment, a partially prestressed section will not be as detrimental as a fully prestressed section, and hence a partially prestressed section is preferable when there is a chance of the reversal of moments. Another important concept we come to know by studying the behavior is the concept of ductility. The ductility is the measure of energy dissipation. For beams, we define the ductility in terms of curvature, and we are denoting this ductility as mu. The curvature ductility is the ratio of the curvature at ultimate, which is denoted as phi u, divided by the curvature at yield, which is denoted as phi y. When we are designing for seismic situations, the ductility becomes an important consideration because for energy dissipation. For prestressed beams, phi y can be defined corresponding to a plastic strain of 0.002 in the prestressing tendons. As we know that for a prestressing tendon there is no definite yield point, then how do we calculate phi y in the moment versus curvature curve of a prestressed section? We have to define a point in the stress strain curve of the steel for which we define a corresponding yield curvature. This point we can select as the 0.2% proof stress point, that is the point with a plastic strain of 0.002. The definition can be changed if we want to have more plastic strain corresponding to the defined yield point. Then we can have a value similar to 0.87 FPK divided by EP plus say 0.005, which gives a plastic strain of 0.005 for the defined yield point. Thus, the definition of yield point for a prestressed section is left to the analyst based on how much plastic strain the analyst wants at the onset of yielding. It has been observed that the ductility of prestressed beams is less than in reinforced concrete beams. That means the ratio of phi u by phi y is less for a prestressed concrete beam corresponding to a reinforced concrete beam. In design of members for seismic forces, ductility is an important requirement. In addition, seismic forces lead to reversal of moments near the supports of beams in a moment resisting frame. Hence, prestressing of beams in a moment resisting frame is not recommended in seismic areas. That means there are two considerations why prestressing may not be helpful in a seismic region. First, the ductility of a prestressed member is lower than a reinforced concrete member. Second, there is a chance of reverse moment acting under seismic forces near the supports of the beams. Hence, prestressing is not recommended for beams in a moment resisting frame. We may have prestressed members in a building which are simply supported, but those members are not part of the primary lateral load resisting frame. The primary lateral load resisting frame should have conventional reinforced concrete beams with appropriate detailing to have adequate ductility and to have adequate capacity under reverse moments. The behavior of a beam and its ultimate strength can be determined by testing prototype specimens. The tests can be conducted under static or dynamic loads. Testing also helps to check the performance of the anchorage units. Whatever we have studied till now was based on analysis, but it is also possible to understand the behavior of a prestressed member and to calculate its ultimate capacity based on experiments, because there can be beams which are prestressed in a non-conventional way, for which the analysis can be difficult. There can be cross sections which are not very easy to compute. In that case, an experimental program is helpful to understand the behavior and to understand its capacity. This photograph shows a prestressed concrete beam being tested in a laboratory. The distributed load has been simulated by 8 point loads along the span of the beam. We see the reaction frame which supports the jacks. The jacks is applying the load on this brown beam, from which it is transferring the load to these blue beams, and finally the blue beams is transferring the loads to the prestressed beam by this yellow load points. Now, in this test, we are simulating the distributed load by a series of point loads, which is more applicable for a bridge structure. And here we see on the right hand side, the anchorage block has been grouted. The section is a flange section, where the flange width is constant throughout the length, but the width of the web has been increased near the ends so as to have less stress concentration at the ends and so as to fix the tendons properly. This is a beam which has been tested to failure to calculate its ultimate moment capacity. Thus, today we studied the analysis for ultimate strength for partially prestressed section. We came to know that many of the times the beams are not fully prestressed. There can be conventional reinforcement along with the prestressing tendon, and we can rely upon those conventional reinforcement for the flexural capacity. There are some advantages of partially prestressed section. First of all, those sections are economical. Next, those sections have more ductility. It is better for reversal of moments, and also if we have reinforcement in a beam with unbonded tendons, then the cracks are more distributed. Now, in the analysis of a prestressed section which is partially reinforced, there are several layers of steel. We have a compatibility equation for each layer of steel. We have the set of equilibrium equations, and we have the set of constitutive relationships. When we solve these equations for ultimate, we can calculate the ultimate moment of resistance for a partially prestressed section. We also studied the analysis of unbonded post-tension beams, and we learned that for an unbonded post-tension beams, we cannot use the strain compatibility equation as we have used for a bonded beams. For an unbonded post-tension beam, the compatibility is based on overall deformation. Thus, it needs an integration of the strain in the concrete at the level of the CGS. The code allows us to use simplified expressions of the depth of the neutral axis and the force in the tendons from the tabulated results. Finally, we studied the analysis of behavior, where we understood the moment versus curvature curve for a prestressed section as compared to a reinforced concrete section. We understood the capacity of ductility, from which we understood the benefits of prestressing and certain drawbacks of prestressing. With this, we are ending the analysis of members, and next we shall move on to the design of prestressed concrete members. Thank you.